Okay, so we're going to begin our review of the topics we've covered so far this year, starting with acceleration. So, acceleration is the rate of change of velocity. And if you remember, we had three ways to accelerate. We could speed up, we could slow down, or we could change directions. All right, now, there is a really important link between velocity and acceleration. They're not the same thing, but the sign of the velocity and the sign of the acceleration together are what ultimately determines if we're speeding up or slowing down. So we are speeding up if our velocity and our acceleration are in the same direction, and we're going to be slowing down if velocity and acceleration are in opposite directions. We have our basic formula for acceleration that simply the final velocity minus the initial velocity over the time. Okay, that rate of change of the velocity. One last thing at this point, I think we're all probably good with this, but the difference between speed and velocity versus acceleration, right? Speed and velocity really is a measure of how fast, and we've said this before, but acceleration is how fast you get fast, okay? Or slow or change directions, but you get the idea. Speed and having a high speed means you're going fast. Having a high acceleration means you're getting fast or slowing down fast. All right, moving on to a few distinctions we need to talk about. Speed versus velocity. If you remember, technically speaking, speed is simply how fast you're going. The velocity, on the other hand, is going to be how fast plus the direction that you're going. Okay, so another way of saying this is that we can say that speed is simply the magnitude of our velocity. The other distinction we need to make is between distance and displacement. Distance is how far an object travels, whereas displacement is how far it is from where it started, or the change in position. And the classic example we used for this was if you run around a track one time, your distance is 400 meters, but your displacement is 0 because you're back to where you started. All right, moving on to some basic ideas about motion graphs, position versus time, and velocity versus time. So just how do we get some basic information? Let's start with that. On a position versus time graph, to get information about the position, we're going to read the graph. To get information about the velocity, we're going to slope the graph. And to get information about the acceleration, we're looking at the curvature, okay? Whether it's concave up or concave down. On a velocity versus time graph, to get that information, for position, we're taking the area, which, keep in mind, gives the change or the displacement. To find the velocity, we're going to read the graph, and to find the acceleration, we're going to slope it, okay? A few other questions to think about. On a position versus time graph, a positive or negative velocity, you're looking for a positive or negative slope. On a velocity versus time, we're looking, is it above or below the x-axis? Okay. Speeding up or slowing down. Okay. On a position versus time, we are looking at whether it is getting flatter or slopier. All right. And on a velocity versus time, we're looking at whether or not it is going towards or away from the x-axis. Lastly, positive or negative acceleration. On a position versus time graph, we're looking at whether it's concave up, in which case it's positive, or concave down, in which case it's negative. And on acceleration versus time, or velocity versus time, we're looking at positive or negative slope. All right, moving on to our kinematics equations here. The one thing to keep in mind here is for these equations, they only work for a constant acceleration. So that is the assumption we're always making with these equations. So there we have our 5 equations written out. All right. Lastly, a few tips for solving these. Should be pretty ingrained into your head at this point, but we're going to set up our chart as always with our 5 different variables here. We're going to be careful with our signs, all right? That's always a key thing. Those are probably the 2 biggest things. It's just being careful with your signs and setting up our chart. That's our basic way of solving these problems. All right, moving on to some concepts about free fall. All objects in free fall are accelerating down at g. okay, at 9.8 meters per second squared. The AP exam, sometimes it's acceptable, not sometimes, it's always acceptable to use 10 instead to simplify calculations, but if you want to use 9.8, that is fine as well. You probably won't see too many calculations on it anyway. Some important concepts that we know. We know at the peak, our velocity is 0. Okay, it's rising up to the peak, slowing down till it hits that point where it stopped for a second as it's changing directions, and then it falls back down. A few other things we know that at the point when it returns to the spot where it was launched, its final velocity is the negative of its initial. Okay, we know that would be if it's symmetrical. We know the time at the peak is half the total. Again, that's going to be true if it's symmetrical. And if it returns to the same spot, its displacement is 0. Again, only if it's symmetrical. Last thing, what is the acceleration at the peak? Well, our acceleration is still equal to 9.8 meters per second squared down. That does not change just because you're at the peak. That is a common misconception, though. All right, moving on to projectile motion. I know we cover this a little bit later chronologically, but it depends on kinematics a lot, so I threw it in here with the kinematics review. Motion in the x direction for projectile motion, that is a constant velocity. Okay, there are no forces in the x direction and therefore no acceleration. And in the y direction, the object is in free fall. Okay, our acceleration is 9.8 meters per second squared down. All right, and those two motions, keep in mind, are independent of each other. Right? It's a combination of the two. A few other concepts here. For horizontal launch, the big one is that our y velocity is going to be 0. Our initial y velocity is 0. Okay, we always, of course, know our acceleration, that the x is 0 and the y is negative 9.8, or like I said, the AP is okay with you using 10 to simplify calculations. For an angled launch, okay, a few things change here. Number one, we're going to have to break that initial velocity into x and y components. All right, v cosine and v sine. A few other things that we know at the peak, our y velocity is 0. That is still true. Whether or not it's symmetrical, that's always going to be true. And then we have our symmetrical concepts. The time here is half the total. All right, only if it's symmetrical. We know that our y velocity here is the negative of our initial y velocity. All right, only if it's symmetrical. And our delta y here is going to be 0. Again, only if it's symmetrical. So you see, those concepts really are exactly the same as they were for free fall. It's just they only apply to the y direction. A few other tips here. Keep in mind that x and y are independent of each other. Okay, there's a good chance you'll see some questions related to that. All right, because they like to ask ones where you have an object dropped and an object fired horizontally. We looked at the dropped and the fired bullet, things like that. The fact that something has an x velocity has no impact on its y motion whatsoever, and vice versa. So that's an important thing to keep in mind here. Other things too, sines is another big one, and then lastly, time is the thing that is shared by x and y. Okay, time doesn't have an x or a y direction, so that does link the two sides.